Hi everyone, what's up? Today I want to show you how to derive the Vis-viva equation. Now this is a really cool equation used a lot in orbital mechanics. So when you have, a star and an asteroid or a planet orbiting the star, this equation is really useful for finding a couple of things about the elliptical orbits. So I'm going to derive it. It's a very important equation. It's very fundamental to orbital mechanics, so we're going to derive it. So first of all, I'm going to start with a setup. I'm just going to tell you like what sort of scenario we have. So say you have an elliptical orbit like this. Let's just say this is an ellipse. Let's say we're going to have what? We're going to have a star here. We're going to have some sort of body A. It could be an asteroid and it's going to be there, okay? So now, essentially, the Vis-viva equation has to do with how much energy this system has, this two-body system has. We want to find, well, we know there's a gravitational potential energy and a kinetic energy. The kinetic energy comes from the orbiting body. And we want to find, well, what is the sum of these two energies, okay? And it turns out that this sum is equal to a constant. There are no external forces acting on this system, so then the energy is conserved throughout the entire orbit. So now we could represent that like this. We could say that epsilon, which I'm going to say is the orbital energy, we're going to say is the following. It's going to be a half r dot. Now r dot is just going to be, hopefully you're familiar with dot notation. Basically, if you have, I don't know, x dot, this is equal to dx dt, okay? Where t is time. So variable dot is just going to be the time derivative of that variable. I'm going to use that notation because it's convenient. And it's usually a convention in orbital mechanics. So we have this, and now we have minus gm solar mass divided by r. Now you're probably wondering, this looks almost similar to what you might have been expecting the total energy is. You may be wondering, well, where is the mass of the orbiting body? We could say m sub a. Where's m sub a? Well, it turns out that this orbital energy is sort of like this. We're essentially saying the ratio of the total energy to the mass of the orbiting body is equal to this. And this is, I think this, we probably call it specific energy, maybe. There's something called specific angular momentum, and we divide by the mass of the smaller body in specific angular momentum, so I guess we could probably call this specific orbital energy. So yeah, because the mass of the orbiting body is really tiny, we can do this. So I'm just going to specify this. I'm probably in here. I'm going to say MA is incredibly tinier than solar mass, okay? So this applies for this scenario. So now we know that the energy is going to be conserved through time and through the elliptical orbit. So then we know this will be equal to a constant. And our goal in deriving the Vis-viva equation, like the motivation for deriving this equation is, if I have information about an elliptical orbit, can I know how much energy this elliptical orbit has? That is the question we're trying to answer. So we're trying to find, well, what can we write this constant? Can we find this energy in terms of information about an ellipse? Now, you know an ellipse, I will assume you've taken some high school math, and you know that an ellipse has some very important values, like its semi-major axis, denoted by A, and the eccentricity, which is denoted by E. Now, the eccentricity tells you how squishy the ellipse is. If you have something like a really violent oval, let's say, or like a really eccentric, that's really the word, eccentric oval, then that's what we call a highly eccentric orbit, basically. And we denote that by E, by just a number that goes from 0 to 1 for elliptical orbits. So we want to write this constant in terms of information like that, okay? Because that information like that describes an elliptical orbit. And we want to know, well, if we know information about the orbit, can we find the energy? That's basically the goal, or sort of like the logic behind this. So, or the other way around, if we know the energy, can we find information about the orbit? And that is actually the most common way you would use that equation. If you have, notice that if you have the position vector of the asteroid, or I'm gonna say it's an asteroid because I called it A, so I'm just gonna say it's an asteroid. If you have the position vector of A and the velocity of A, which are things you could measure with a telescope, if you have these vectors measured from the sun, which you have to do some math for that, but it's possible. If you have these vectors from the sun of the asteroid, then you could find how much energy there is. And using the Vis-viva equation, you could also find how much. You could also start to describe this orbit in more detail. Okay. So now let's do the math, which is probably what you want to see. So since this is a constant, well, I'm just gonna rewrite this into constants. So I'm gonna use a couple of equations that are pretty important. So first, I'm gonna say that the perihelion Q, the perihelion is gonna be the point in an orbit in which the orbiting body is going to be closest to the star. So in this case, in this scenario that I drew here, well, it looks like the A is gonna be closest to S, probably here, like I don't know, around this point, the length of the arrow. So then Q, this is just standard for all ellipses. Q is gonna be A times 1 minus E. A is the semi-major axis, E is the eccentricity. Now, another equation that I am going to need is the following. If you want to write an ellipse in polar coordinates, I'm not going to prove this, but this is something you can do just by changing the coordinate system. If you want to write r as a function of some angle in polar coordinates, you're going to have L, a constant, and I'm going to show you what that is in a moment, 1 plus eccentricity cosine theta, okay? So this is an equation for an ellipse. And it turns out that we are really interested in this constant L, and it just turns out that this constant L is going to be equal to, can I do it here? I think I should probably do it here because it's going to be really relevant. So I'm going to do it down here. L happens to be equal to H. I'm going to tell you what H is in a moment. H squared actually, divided by GM solar. And this will be equal also to semi-major axis 1 minus eccentricity squared, okay? This is a very important equation. Proving this is really hard. It takes like an hour to prove this. I might make a video on this at some point, but for now just know that this is true, okay? This is Kepler's first law. If you derive Kepler's first law from Newton's second law, which takes like an hour, you're gonna get that L, this constant, you're gonna get this first, and then to find L, you can do a lot more math, and you're gonna get this, okay? So then this is something, this is true, okay? And we're gonna use it. So another thing that I should, like another condition or thing that we're gonna use is we're gonna define a dummy variable, which I'm gonna call mu, and mu is gonna be GM solar, okay? Now this is conventional in orbital mechanics. Usually you have a lot of GM solar, so we use mu instead. So now let's do this. So if we want to rewrite this expression, the kinetic energy and the potential energy, in terms of more stuff, well, we can do, oh, I didn't explain what H is. Yes, so H, very important, yes. So if we want to rewrite this, we're going to have to use H. Now, if you've taken some physics or some orbital mechanics before, you know that H is going to be a vector, and it's what we call the specific angular momentum. Again, this is sort of like doing H divided by the mass of the asteroid is going to be R cross R dot, okay? So R position vector of A and R dot velocity of A, if you multiply through MA, well, you're going to have R cross P, the traditional P that you know. But since MA is really, really tiny, we just erase it. And this simplifies calculations a lot. And symbolically, it looks better. So this H squared that you see there, well, H is just going to be, this is the magnitude of this vector. That's the notation that I'm using. So I'm going to say that H, another definition that we want to keep in mind, is going to be R times R dot sine theta, okay? It's a cross product, so this is the magnitude of a cross product, and theta is the angle between R and R dot. So now let's use this information to rewrite this epsilon. So we know that epsilon is going to be a half times r dot square. Now, notice we have an r dot here and we have h. And we also have h here. L, fun fact, this is called a semi-lattice rectum, I think. Semi-lattice rectum, I think that's the name. It's a really weird name, but yeah. Now, we have h in the equation for L. And we also have h in terms of this, which this, contains information about an orbit, which is what we want. So we're gonna do the following. We're gonna rewrite r dot in terms of other things like this. So we're gonna say, I'm gonna do it here, I think. R dot then is going to be h divided by r. And I'm gonna do something that's pretty clever. Because the energy is conserved at any point, like throughout the entire orbit, we could pick any r that is convenient, or we could evaluate, I'm gonna do it like this. We could evaluate the orbital energy at any point, and I'm gonna say that we're going to evaluate it if, energy is a function of r, which it really isn't, but we could use this notation. We could say that the energy at the perihelion is going to be the following. So then it's gonna be a half times the speed at the perihelion divided by, minus mu divided by the perihelion. So we could do the following. We could do a half, and now we could let this r be equal to q. Now this is the equation for the definition of specific angular momentum. So then we have h divided by q. Now what about sine theta? Well, in an ellipse or in a circle, hopefully you know this, the position vector is always going to be perpendicular to the velocity vector. You can prove this by just parametrizing a circle or an ellipse and then taking the derivatives and doing dot products. You're going to see that sine theta is going to be 1 at the perihelion point, okay? And that's just, that it's really nice because then we just get 1. So then r dot is equal to this here, okay? Which is convenient. So then we have r dot is going to be equal to this, and we want to square that. So we're going to have h squared divided by q squared. Let me write that again. And yeah, that looks better. I thought the previous time was a little too tiny. So yeah, so we have h squared divided by q squared. And now we're going to have minus mu divided by r equals q, right? So q. Nice. So now we can just plug and chug, sort of. We're going to have h squared. Well, using this definition, we know that h squared is going to be gm solar times this. Now we know gm is going to be mu, so we're going to have the following. We're going to have, I'm going to write it like this, a half times, so the numerator of this is going to be mu gm. I'm just moving gm to the right hand side of this equation. Mu a times 1 minus eccentricity squared. Okay, remember a is the semi-major axis. We're going to be dividing by q. Q is equal to this. This is something you can derive by just looking at an ellipse. Looking at the basic math of an ellipse gives you that. So you're going to have a squared 1 minus e squared. Okay, and the second term, mu divided by q. Okay, so you say, well, oh, not q actually. I'm going to write this. Let me do that again. I'm going to write this using, well, the definition, not really the definition, but the equation for q. So this is going to be a 1 minus e. Okay, so nice. So we have this. So now we just simply need to simplify a couple things, and this will be a really nice constant in the end, and you're going to see what it is in a moment. So we know this a goes away with this one, and we're going to expand these two factors like this. So we're going to do, this is just math, really. If you're good at math, you can probably tell really easy what it is that I'm about to do. This is 1 plus e, 1 minus e. Here I'm just expanding this binomial. And here, well, we have 1 minus e times 1 minus e minus mu a 1 minus e. Okay, so again, nice canceling here. We're gonna get, so yes, I will, oh, and I missed something. Hopefully you saw that I missed an A there, okay? So yes, there's an A right there. That looks like a 9. Nice, that's an A. So then notice that we have a common factor here. We have mu divided by A times 1 minus E, and mu divided by A times 1 minus E. We're going to factor that out. We're going to get the following. So we're going to get that epsilon evaluated anywhere. I could keep using the evaluated at Q, but it doesn't matter really. So epsilon, and actually let me do this a little further below, like probably here. Epsilon is going to be equal to, so we're factoring out mu, A, and that 1 minus E. So we have mu A times 1 minus E. And now that is going to be equal to a half times this. So let's say this is a half times 1 plus E. 1 plus E. And then we have minus 1. We keep going, so this will be mu A times 1 minus E. Now this will be a half plus E divided by 2 minus 1. So we have a half minus 1. That's going to be negative a half. So we have E divided by 2 minus a half. Now I'm going to do something nice here. Notice that if I factor out a negative 1, I will have 1 minus E, and then I will be able to cancel it out with this 1 minus E in the numerator. So then I'm going to factor out from here a negative a half. So then we have minus mu divided by 2A 1 minus E times 1 minus E, okay? So the signs flip here. Negative 1 becomes 1, E becomes negative E. And we have this. And again, these go away. And you can see very nicely that the orbital energy is going to be minus mu divided by 2A, okay? 2 times the semi-major axis, okay? Very nice. So we have this, and we know this is going to be equal to a half r dot squared minus mu divided by r. Now typically we look at twice the orbital energy for reasons I guess just symbolically looks better. So I'm going to multiply this by 2. So I'm just going to have this minus mu over a is going to be equal to r dot squared minus 2 mu r. Is that right? Yep, that's right. So then the Vis-viva equation, it's essentially this, just solving for r squared. That's typically how we do it. So r squared is going to be, I'm going to factor out a mu from there. So we're going to have mu times 1 over r, wait, yeah, this becomes positive. So we have 2 over r, I'm sorry, 2 over r minus 1 over a. And this is the Vis-viva equation. It's very nice, and I'm gonna say a couple more things about it. So this is the Vis-viva equation. Vis-viva is a term in Latin that stands for living force, and I think this was discovered by Leibniz. He basically saw that the quantity, I think it was mv squared, was conserved throughout like physics problems. Like if you do a physics problem, in many scenarios you're gonna see that energy is conserved, assuming you don't have external forces, work, and all that. So Vis-viva, and Leibniz called that energy or thing living force. He called that quantity mv squared living force, or Vis-viva. So this is where the name comes from. Now this is very nice. This equation is very powerful because it tells you, so basically in astronomy, if you're trying to describe the orbit of a celestial body, you're going to make observations using a telescope. And those observations, you're going to collect a lot of data with those photos and images that you take of the celestial body. And with those images, you can calculate, using very sophisticated methods, you can calculate a position and a velocity vector. With those vectors, you can find their magnitudes, and using this Vis-viva equation, you can solve for the semi-major axis of the orbit of the celestial body, okay? With the semi-major axis, you can do so many things with the with the orbit of the object that you're dealing with. You can find eccentricity. You can find many other. Usually, we use a lot of angles to describe orbits. So with A and with E, you can find all those angles that describe an orbit. Those are what we call the orbital elements of an orbit. If you've taken some orbital mechanics or you know some things about that, you probably know that A and E are two of the orbital elements, and you need those two elements to find the other four elements. There are six in total. And well, once you take observations with a telescope, you find a position and a velocity vector, and with that you find A, okay? And you do that with this equation, the Vis-viva equation. It's pretty nice. Now, some complaints you may have. I did not prove. I didn't prove this, although this is kind of like just the math of an ellipse. There's really, I mean, yeah, I guess you could prove it, but really the physics part comes here. Using Newton's second law, you can show that this is true. I did not prove this. I will probably make a video on this, but for now you can Google it. This is right. I definitely did not prove this. This is really long to prove. It hurts to prove this. It's like an hour. It's really long, and I would need a couple of boards to do it. Maybe I'll do it at some point. Hopefully I'll do it, yes. This is just a definition. I guess you could probably do this. Oops. Yeah, that looks better. So this is just a definition. These are also just definitions and things that don't need a proof. Yes, that's what you have. I hope that this derivation has seemed convincing. I understand that we need to prove this. You can prove it using Newton's second law and a lot of time. You need time to do this. But yes, I will upload videos on this proofs at some point. I hope so. So yes, this is nice. This is the Vis-viva equation. Hopefully you liked it. All right, bye.